In this lesson, we discuss how to take that vector space model and assign each document to a small number of groups, called clusters. The basic idea is that documents within a cluster should be similar to each other, and documents in different clusters should be dissimilar to each other. The similarity between two documents is based on the similarity of features, such as terms or words, between documents in the vector space model.
The key idea in applying clustering technique to a group of objects is to identify, if any, groups or clusters of objects such that the objects within a cluster are similar but the objects between different clusters are dissimilar. As a simple example, in a class of students, the natural clusters will be male and female based on the attribute gender. The example shows 7 objects with different values of their attributes of shape, color, and weight. In the example, note that if we use only the attribute color, we get only 2 clusters. If we use only attributes color and shape, we get 4 clusters. How many clusters will we get if we used the attribute weight for clustering? 3 clusters. Did you get it correct? Points to note: so we see the outcomes derived from clustering depends on what attributes are being used for differentiating the element of dissimilarity. Note that an object identified can only be in one and only cluster. The clusters are mutually exclusive. This means that objects in a cluster are distinctly dissimilar from objects in other clusters. Clustering is usually used in the initial phase of a data mining project for exploratory of data characteristics. There is no predefined themes or classification upfront. The discovery of distinct clusters, if any, is purely unsupervised. Clustering approach is widely used in different sectors of the industry. For example, in marketing, clustering may be used to identify clusters of customers' behavior and profiles towards different brands of products. With such information, marketing campaign can be more targeted. In insurance, clustering can help to identify profiles of customers who has the tendencies to default premium payments. Clustering is also helpful in groups of people who lives in certain geographical location or house type. This is useful for policy makers in city planning. In this short video, we want to look at how clustering is done using SAS Enterprise Miner.
Hi, my name is Catherine Truxillo and I'm with the Statistical Training Services Division at SAS. And today is part 1 of a 2-part SAS training video tip on using the segment profile node in SAS Enterprise Miner. So I've got here a simple example, and it's commonplace that people perform some kind of cluster analysis in order to segment their population into groups. And once you've done that segmentation, the next order of business is to perhaps decide how many clusters you should use or to come up with some meaningful description of those clusters. And those 2 jobs are actually inextricably linked. But if you have a lot of input variables, it can be very, very difficult to get a good idea of how each cluster differs from the overall population. And so things like doing pairwise comparisons of your clusters falls short because you're just comparing clusters to one another. Here we're going to actually be able to compare clusters to the overall sample. So I've got a simple cluster analysis going on here, and with this simple cluster analysis, I'll talk you through it while I run this entire diagram. In this cluster analysis, what I've got is some census data, and I'm using 3 input variables to try to define my clusters. I've got 3 clusters specified, and the clusters are based on population density, household size, and household income. Now, when I'm profiling those clusters, I don't have to use those same 3 variables. In this case, I will, but you can actually profile your clusters using any variables that would be useful for description. So in the Assess tab is the segment profile node. I'm going to drag that down and connect it. Make it so you can see this just a little bit better. And I don't want to just run this right out of the box because there are some variables in here that I need to turn off. I don't want to have my segments profiled on some of the variables in my data set. For example, the distance, I don't want to use that one. I'll go ahead and turn off some of these variables that I don't want to use and leave behind just the variables that I am interested in using. So click through those, make sure everything is set the way I want it to be, and now I'm ready for action. You'll notice down here there are some settings, and I'll keep my mouse off of them so it doesn't obscure your ability to read these, but one of the things is you'll see for input variables that there's this minimum worth. That's a threshold or a cutoff for determining whether a variable is worth enough. It's based on, it depends on what statistic you're using. In this case, it's using a log worth statistic, but it is determining whether a variable is useful in being able to differentiate a cluster from other clusters. And it has that threshold there that you can set. Once it completes, we're going to take a look at the results. There are 3 sets of graphical output and 1 bit of summary statistics in the output here. What I really want to focus on are these overlaid histograms, but just briefly what we've got a pie chart showing the size of the segments, so the number of observations in each group. I've got 19,000 in segment 3, got more or less 9,000 in segment 2, and I've got about 2,600 in segment number 1. I've also got these bar charts of the worths of the variables for each segment. This is each variable's contribution to the ability to be able to differentiate that segment from the rest of the overall sample. So for segment number 3, far and away the winner is household income. For segment number 2, household income is also a big differentiator. For segment number 1, it's household size. These are arranged in order by decreasing size of the segments. And if I expand this, you'll notice there's only one variable that characterizes segment number 1. That's because none of the other variables exceeded that minimum worth threshold of 0.01. You can change that threshold. You can make it smaller to let more variables in. You can make it higher to let fewer variables in. In this case, it corresponds roughly to a p-value. It is not the same as a p-value, but it is a function of the p-value. Here we've got segment number 3, which seems to be mostly characterized by having a fairly low median household income relative to the overall sample. Now you ask, how do you know that? The way I know that is because I've actually got 2 overlaid histograms here. The red histogram is the overall sample. You can see if you look down these 2 plots, they have the same red histogram. The blue histogram represents the segment in that row. So segment number 3, the blue bars, are lower in overall household income than the overall sample. The second variable that characterizes segment 3 is region population. You can see these are fairly low population density groups or observations, and the average household size is just a little bit less than the rest of the population. All of the large households seem to be in other segments. For segment number 2, it's mostly characterized by having high median household income and high population density and a fairly high average household size. Finally, segment number 1 is mostly characterized by a high average household size. That is the variable that mostly characterizes it. This scales well to a very large number of variables. It also scales well to cases where you're profiling your segments based on variables that were actually not used in the cluster analysis, which is another way of validating your segments, of whether they have some kind of face validity. I hope you've enjoyed this tip. This tip is actually from the Advanced Analytics for the Modern Business Analyst course. And next time I'll be talking to you a little bit more about some other nifty tricks that you can do with the segment profile node. Thanks for watching.
Given a corpus of document collection, clustering can identify documents of similar themes. For example, in a corpus of a few thousand documents, some documents may have themes relating to healthy living, financial management, or a particular sports like playing soccer. Instead of identifying themes in each document in the corpus and group the documents according to the same theme, the clustering algorithm may identify topics of interest by examining documents that have similar sets of words. A topic is a group of words that co-occur in many documents. For example, in many documents in a corpus of hotel customers' feedback, the word toilet always appear with the word small. That could be a strong indication that the common complaint is that the hotel room's toilet is too small. In the context of text mining, clustering divides the document collection into mutually exclusive groups based on the presence of similar themes. In most business applications involving large amounts of textual data, it is often difficult to profile each cluster by manually reading and considering all of the text in a cluster. Instead, the theme of a cluster is identified using a set of descriptive terms that each cluster contains. This vector of terms represents the weights measuring how the document fits into each cluster. Themes help in better understanding the customer, concepts, or events. The number of clusters that are identified can be controlled by the analyst. For example, we want to find out the themes in the patient's comments about their experience in a particular hospital. The clustering results from text mining. The comments come out similar to the ones shown on the slide. There are 3 clusters. Each cluster can be described by a set of terms, which reveal, to a certain extent, the theme of the cluster. This type of analysis helps businesses understand the collection as a whole, and it can assist in correctly classifying customers based on common topics in customer complaints or responses. Based on last example, how do we actually identify which keywords goes into which cluster? We need some objective metric or measure to decide the degree of similarity of words for a cluster. In statistics, similarity is often measured via 3 broadly defined methods: distance, correlation, and association. In distance-related methods, if 2 things are similar, the distance between them must be small. If 2 things are dissimilar, the distance between them must be large. There are many distance metrics in statistics literature. Commonly used ones are Euclidean distance. In correlation-based methods, such as cosine similarity, high correlations indicate similarity, correspondence of patterns across variables, between objects, documents. Low correlation indicates dissimilarity between objects, documents. Correlational measures represent patterns rather than magnitudes. An association metric generally assesses the degree of agreement or matching between 2 pairs of observations. The simple matching coefficient, which measures the percentage of times that the 2 objects match in variables, is an example of an association measure. Although these metrics are often intuitively appealing, for most practical document clustering problems, the term by document matrix is too large and too sparse to effectively apply these metrics. Although most clustering algorithms for data mining of structured data is applicable to text mining, some of them are not effective for text mining due to high dimensionality of data points or words. Text clustering algorithms are split into many different types such as agglomerative clustering algorithms, partitioning algorithms, and probabilistic clustering algorithms. Clustering algorithms have varied trade-offs in terms of effectiveness and efficiency. In this module, you are not expected to know the details of how these algorithms except for a high-level ideas of they works. In hierarchical clustering, in the top-down approach, we begin with one cluster which includes all the documents. We recursively split this cluster into subclusters. In the agglomerative approach, bottom-up, each document is initially considered as an individual cluster. Then successively, the most similar clusters are merged together until all documents are embraced in one cluster. K-means clustering is one of the partitioning algorithms which is widely used in the data mining. The K-means clustering partitions n documents in the context of text data into K clusters. The main disadvantage of K-means clustering is that it is indeed very sensitive to the initial choice of the number of K. Topic modeling is one of the most popular the probabilistic clustering algorithms which has gained increasing attention recently. The main idea of topic modeling is to create a probabilistic generative model for the corpus of text documents. In topic models, documents are mixture of topics, where a topic is a probability distribution over words. Watch the next video on hierarchical clustering.
Welcome back to Mining of Massive Datasets. We continue our discussion of clustering by looking at hierarchical clustering methods. To refresh our memory, in hierarchical clustering, we can either go bottom-up or top-down. In bottom-up methods, each data point is initially in a cluster of its own. At each step, we find the two closest clusters and combine them into a single cluster. In divisive methods, all the data points are in a single cluster to begin with, and we recursively split the cluster as we go along. In this lecture, we're going to focus on the agglomerative or bottom-up approach, where we start with each data point as its own cluster and then combine clusters. The ideas in the lecture can be easily adapted to divisive methods as well. The key operation in hierarchical agglomerative clustering is to repeatedly combine the two nearest clusters into a larger cluster. There are three key questions that we have to answer in order to build a hierarchical clustering algorithm. Those three important questions are the following. How do you represent a cluster of more than one data point? We need a representation of a cluster so that we can figure out which clusters are close to each other. And that brings us to the second question, which is how do you determine the nearness of cluster so that we can combine the two nearest clusters? And the third question is, as we keep going along and combining clusters, when do you decide to stop and produce a final output? So we look at each of these three questions in turn. Let's start with a simpler case of a Euclidean space. In a Euclidean space, we can always average 2 points, and the average is also a point in the Euclidean space. This gives us a simple answer to the question of how do you represent a cluster of many points. We can represent a cluster by its centroid, which is the average of its points. And to determine the nearness of clusters, we just measure the cluster distances by measuring the distances between the centroids of the clusters. An example will make this clear. Here we have 6 points in a Euclidean space. These O's represent data points in a Euclidean space, and we're going to apply an agglomerative clustering methods. Initially, let's say we determine that these points 1, 2 and 2, 1 are the closest points. We combine them into a single cluster, and now we're going to represent this cluster by its centroid. To compute its centroid, we have to compute the average of the 2 points, which is just the average along every dimension. So the average of the points 1, 2 and 2, 1 is the point 1.5, 1.5, which is the centroid of this newly created cluster. Now we have 5 clusters. Remember, we started out with each data point as its own cluster, and we've combined 2 of the data points into a single cluster. So now we have 5 clusters. Now we need to find the nearest pair of clusters. And as it turns out, the nearest pair of clusters is the pair of points 4, 1 and 5, 0. And once we've created this cluster, we then represent it by its centroid. Now the centroid of this cluster is the point 4.5, 0.5. Now the 4.5 is obtained just by averaging the x coordinates of the 2 points, and the 0.5 is obtained by averaging the y coordinates, which are 1 and 0. So now we have 4 clusters. Okay? And as we go along merging clusters, we create this artifact called a dendrogram. And the dendrogram shows how we merge data points and clusters as we go along. In the first step, we merge the 2 blue data points, and in the second step, we merge the 2 green data points, and that's what the dendrogram indicates. Now in the next step, we determine that the 2 closest clusters are the cluster with centroid 0, 0 and the cluster with centroid 1.5, 1.5. And we can measure, we do this just by measuring the distance between 0, 0 and 1.5, 1.5, and finding that to be the shortest distance between any pair of clusters. Once we do that, we can combine the 3 points 1, 2, 2, 1 and 0, 0 into a single cluster, and we can represent it by its centroid, which is 1, 1. Now to determine the centroid of this combined cluster, we have to average all 3 points 1, 2, 2, 1 and 0, 0. And the average in the x in the x axis is 0 plus 1 plus 2, which is 3 divided by 3, and that gives you 1. And similarly along the y-axis. So now we have 3 clusters, one cluster with centroid 1, 1, another with centroid 5, 3, and a third with centroid 4.5, 0.5. And when we measure the intercluster distances between these 3 centroids, we determine that the 2 closest are 5,3 and 4.5, 0.5. So we can combine those, and that new cluster has centroid 4.7, 1.3. Now we are reduced to 2 clusters, and we have no choice at this point but to merge these 2 clusters. So either we can stop at this point and output these 2 clusters, or we can decide to merge them further and create a single large cluster. And now a single cluster doesn't make a lot of sense, because our goal was to end up with group the points into many different clusters. But on the other hand, even if we do merge these 2 clusters and create a single large cluster, the dendrogram actually shows the order in which these the merges happen, and it contains very useful information in many cases. For example, if the data points actually represent species of different animals, then the dendrogram represents a family tree of how these species evolved. Now that was the easy or Euclidean case of hierarchical agglomerative clustering. But what if we have a non-Euclidean space? The problem with a non-Euclidean space is that it's not possible to average points and create a centroid. The centroid may not be a valid point in the non-Euclidean space. So the only points or locations we can talk about in a non-Euclidean space are the points themselves. There is no concept of average. and therefore we cannot continue using the centroid to represent a cluster. So instead, we have to use a different concept called a clusteroid. And a clusteroid is a data point that's closest to the other point in the cluster. So once we use clusteroids instead of centroids, and we look at an example of clusteroids in the next slide, we can determine the nearness of clusters by treating the clusteroid exactly as if it were the centroid. And we can measure the distance between two clusters by measuring the distance between their clusteroids instead of measuring the distance between their centroids. Here's a cluster on 3 data points in a Euclidean space. Now, the centroid, which we saw how to compute, is just the average of all these data points in the cluster. The X here marks the centroid of the 3 data points shown. Notice that the X is actually a data point that was not among the original 3 data points in the cluster. It's an artificial point that we created to represent the cluster. Now, the problem in non-Euclidean spaces is that we cannot create this artificial point, and therefore we just have to pick one of these 3 points as a clusteroid to represent the cluster instead of using X, the centroid. So in this case, for example, we might pick the point shown as a clusteroid to represent the cluster, because intuitively it's in the middle of the cluster and it's close, and it sort of seems to be equidistant from the other points, and therefore we might pick the highlighted point as a clusteroid. Notice that the clusteroid is actually an existing data point. It's not the centroid, but for all practical purposes, we can treat it as a centroid in clustering algorithms. Now, we've defined the clusteroid to be the point that is closest to the other points within the cluster. Now, how exactly do we define this notion of closest point? It turns out that there are multiple ways of defining the notion of closest when we are picking the clusteroid. For example, we might want to pick the point that is at the smallest maximum distance to other points, by which we mean we measure the distance between every pair of points, and then we find a point such that the maximum distance between that point and any other point in the cluster is as small as possible. Instead, we might look at the point with the smallest average distance to the other points. Or we might look at the point with the smallest sum of squares distance to other points and pick that as a clusteroid. Depending on the application, one or the other of these notions of clusteroid might make more sense than the others. So far, we've addressed the first 2 of the 3 key questions of clustering. The first being, how do you represent a cluster? And the second being, how do you determine the distance between clusters? We now turn to point 3, or the termination condition. How do you know when to stop clustering and produce an output? The first approach is to pick a number k up front and stop when we have k clusters. Now, this approach makes sense when we know up front that the data falls naturally into k classes. For example, the data might be about galaxies and quasars, and we know that there are naturally 2 classes, galaxy and quasar, and once we have 2 clusters, we stop. The second approach, when we don't know the number k up front, is to keep clustering and stop when the next merge of clusters would create a bad cluster. Now, how do we define a bad cluster? We define a notion called cohesion, which measures the goodness of a cluster. And when the cohesion value falls below a certain level, we've created a bad cluster. And we stop when the next merge would create a bad cluster. How exactly do we define this notion of cohesion? There are multiple approaches to defining cohesion. The first approach to cohesion is to use the diameter of the merge cluster. Now, the diameter of the merge cluster is the maximum distance between any pair of points in the cluster. We might decide to stop clustering when the diameter of a newly merged cluster exceeds a certain preset threshold. The second approach is to use radius. The radius is the maximum distance of a point from the centroid or the clusteroid. And we might decide to stop clustering when we would produce a cluster of greater than a certain threshold radius. The third approach is to use a density-based model. Now, density of a cluster is the number of points per unit volume of the cluster. One way of defining density is to simply divide the number of points in the cluster by the diameter or the radius of the cluster. We might instead divide the number of points by a power of the radius, such as a square or a cube. And at a point where the next merge would create a cluster with a density lower than a certain preset threshold, we'd stop merging and produce a final output. Notice that in each case, we set a predefined threshold either for diameter, radius, or density, and stop when the next merge would violate that threshold. We turn now to implementation of hierarchical agglomerative clustering. At each step in hierarchical clustering, we need to find the closest pair of clusters and merge them. In order to find the closest pair of clusters, we need to compute pairwise distances between all pairs of clusters. Since we start with each point in its own cluster initially, there are order n clusters where n is the number of points, and therefore computing pairwise distances takes time order n squared. Overall, we might have to do order n steps of merging, and therefore the overall complexity of hierarchical agglomerative clustering is order n cubed. Now, if we do a careful implementation using priority queues, we can reduce the complexity to order n squared log n. N squared log n, though, is still too much for really big data sets that don't fit in memory. When n is of the order of millions, order n squared log n can get out of hand pretty soon. That's why hierarchical clustering is not commonly used for really big data sets that don't fit in memory. It's primarily used for small data sets that do fit in memory. When you have really large disk resident data sets, we use other methods of clustering, which we turn to next.
Although k-means is a very popular and widely used algorithm for clustering numeric data and is available as a node in SAS Enterprise Miner, it is not currently used in SAS Text Miner. Watch the next 2 videos on k-means clustering. The expectation maximization (EM) algorithm is one of the most well-known and effective techniques for estimating mixture models. The EM algorithm assumes a probability density function, typically joint normal distribution, of the variables in each cluster. Then, the algorithm applies an iterative optimization to estimate the probabilities for each observation to belong to each cluster. EM algorithm consists of two steps, the expectation, E, step and the maximization, M, step. In the expectation, E, step, input partitions are selected similar to the k-means technique. In this step, each observation is given a weight or expectation for each partition. In the second step, maximization, M, the initial partition values are changed to the weighted average of the assigned observations, where weights are identified from the E step. This cycle is repeated until the partition values do not change significantly as identified by the log likelihood of the iteration.
Hi everyone, in this video we discuss how to use the text cluster node in SAS Enterprise Miner. The text cluster node clusters documents into disjoint sets of documents and reports on the descriptive terms for those clusters. Two algorithms are available. The expectation maximization algorithm clusters documents with a flat representation, and the hierarchical clustering algorithm groups clusters into a tree hierarchy. Both approaches rely on the singular value decomposition or SVD to transform the original weighted term document frequency matrix into a dense but low dimensional representation. See more details of these algorithms in SAS Text Miner reference help. Typically, the hierarchical method is more popular. Basically, text cluster works similarly as cluster analysis in multivariate statistics. The difference between text cluster and text topic is that text cluster assigns each term to a unique group, while in text topic, terms can belong to more than one topic or none at all. So if you are developing taxonomies for a certain research issue, you can decide whether to use text cluster or text topic. In this example, suppose we want to develop clusters for terms from the document collection. Accordingly, we do not use the target variable since the purpose of this example is not about predicting the target variable. In order to use the text cluster node, on the text mining tab, select and drag a text cluster node into the diagram workspace. Then connect this node to the text filter node. On the properties panel, in the cluster group, we select hierarchy method for cluster algorithm. More details on cluster algorithms can be found in SAS Text Miner reference help. Let's run this node. Right-click at text cluster, select Run, and click Yes. The run is completed. Select Results. There are several results we can examine, but I recommend focusing on the cluster frequencies pie chart, the cluster table, and the distance between clusters scatter plot. The cluster frequencies pie chart shows the frequency of each cluster. Position the mouse pointer over a sector to see the cluster ID and frequency in a tooltip. Select a sector to highlight the cluster in the other graphical results window and the cluster table. For example, in this case, we have 6 clusters. If we move our mouse pointer to the red piece, we see that this is cluster 6 with the frequencies of 17. By selecting this cluster, it also highlights the same cluster in other results such as cluster table or distance between clusters scatter plot. The cluster table displays information about each cluster, including descriptive terms that make up that cluster, frequency, percentage, coordinate, etc. The distance between clusters scatter plot shows the distance between clusters using a Cartesian coordinate system. Position the mouse pointer over a point to see the x-coordinate, y-coordinate, cluster ID, and descriptive terms in the cluster in the tooltip. The higher the distance between the clusters, the better, since this indicates the uniqueness of these clusters. Overall, the text cluster node provides us 6 unique clusters, and the details of each cluster are presented in the clusters table. We can use these clusters to develop taxonomies for specific research issues. The descriptive terms for each cluster allows us to understand and describe these clusters for our research purpose. That is how to use the text cluster node in SAS Enterprise Miner. Thank you, and bye now.
So in this short presentation, we have briefly covered what is clustering technique and it is applied to text mining process. Do not forget to do the lab exercise for this session.